had said that machine learning can be broadly categorized into 3 categories. Those are supervised learning, reinforcement learning, and unsupervised learning. So in the past few weeks, we've been tackling supervised learning. That's where we have a data set that is labeled. And in a nutshell, supervised learning is basically an attempt to try and predict the labels using machine learning algorithms. So today in unsupervised learning, the paradigm shifts a little bit. So we'll be working with data that is not labeled in any way. And it will be our responsibility to group this data into categories depending on their similarities. So basically that's an overview of what you're going to do today, but let me give you a better intuition into unsupervised learning. So I'm going to share my screen here. Yeah, so this is basically what you're going to touch on. So if we simply define unsupervised learning, it's an approach in machine learning where we just given observations. They're not labeled in any way, and so you don't have any way of determining what the category of the data is or what the output of a given observation is in the case of regression. So common methods used in unsupervised learning include clustering and principal component analysis. So clustering is just what I mentioned some few minutes ago, and it's basically the grouping of observed instances into categories or clusters based on their inherent characteristics and specifically their inherent similarities. So what I mean is that given a number of observations, we want to take observations with common features and put them in one category, and other observations with different features from the one that we've already clustered, we'll then cluster them in different categories. So we'll see much of that later on. And then the second common method used in unsupervised learning is principal component analysis. So this is common in places where we have high dimensional data that is not labeled. And so our objective is to try and reduce the dimensionality of this data such that we only pick elements that are of interest or which bear significant weight to our data. So think of PCA as a bottleneck or a sieve that takes in data that is high dimensional in terms of maybe the number of columns. Maybe you have 50 or so columns. So what PCA does, it will go through all these columns and then try and find the most relevant information from these 50 columns and compress it into, say, 2 or 3 columns. So you can evaluate your PCA's effectiveness using something called explained variance. So of course, best PCA models have got a higher explained variance. So you want a PCA that has as few as possible number of components, which explain as much variance in the data as possible. So today, our main focus will be on clustering. If time allows, probably next week, we may look on principal component analysis. But today, specific interest will be on clustering. So algorithms that are commonly used to perform clustering include agglomerative clustering over here, hierarchical, then there is the density-based methods, and then you have k-means algorithms. So of these 4, k-means is perhaps the most commonly used algorithm, and for that reason, that is what today's session will be on. So here I'm just explaining how k-means works. So it achieves clustering by grouping observations into k different categories. So k is just a predetermined number that will pass, and then our algorithm will try and cluster the observations into those k unique groups. So of course, the grouping is based on Euclidean distances. You remember from our previous class, we had touched on k nearest neighbor. So one principle of operation for k and n is that it uses geometric distances like Euclidean to find the most proximal neighbor. So the same principle is applied here, but instead of finding the most the most probable neighbor, we are interested in the most closest cluster in which we can categorize a new observation. And the way we do this is by classifying an observation depending on how close it is to a given centroid or to a given cluster. So what I'm trying to say is, if you have like 5 clusters, if you have like 5 clusters, we are going to categorize our observation into a cluster that is very close to our new observation. Okay, so if you are keen in the previous class last week, it's basically the same process, but now it's more of clustering than classification. So of course we need to bring in some equation here. So basically what this equation represents is that it represents the objective function that you're trying to minimize. Remember, we want to optimize the distance between an observation and a given centroid. So to do that, this is the guiding equation. So basically it's the sum of all Euclidean distances for pairwise points. So that's why you have an absolute 2 here for all instances in S that belong to Si. So given Si observations, we want to find the sum of their pairwise distances, which is given by x minus y in a Cartesian coordinate. And then we want to minimize that so that we can find the appropriate cluster for a new observation. So here I had mentioned that the clustering is achieved by grouping observation into k unique groups, where k is a predefined number of clusters. So the question is, how do we select the optimum number of k? So there are different approaches that can be used to do this. We can either use inertia method here or the distortion methods. So basically what the inertia value represents, it's a representation of the distance from one observation to the mean of a given cluster. So it's such a pity that we don't have an image of clustering here, but let me just get you one quickly. Just a moment. Yeah, I think this is better. So what I was trying to say is that we have two distances. We have like the distortion value and the inertia value. So what distortion measures here, I'm saying it's the distance, what inertia measures, it's the distance from one observation to the mean of its cluster. So given these two images, of course, the dots are observations. So we can approximate that the mean is somewhere in between this circle. So what inertia does, it will take the sum or the average of the distance from this cluster to the mean, this cluster to the mean, this cluster to the mean, and so on. And then it will do that for cluster 1, 2, and 3. So it's going to give us distortion distances for those clusters. On the other hand, we have this distortion value over here, and I've defined it as the average of the squared distances from the cluster centers of the respective clusters. So basically, we have a center for cluster 1 here, cluster 2, cluster 3. So we're going to get the differences, square them, and then find the average, and then we will return that as a distortion value. So these are the two metrics or matrices that you can use to select the optimum number of k. And I'm going to show you how that can be done in a moment. So it's done through something called an elbow curve. Basically, given a certain range of clusters, we are going to get an elbow curve, and then from this curve, we'll be able to determine the best number of clusters. So finally, I want to conclude by saying that clustering in itself, it's kind of iterative, and the iteration occurs because our main objective is to converge the distances between the centroids. So we want to repeat the process of finding a centroid until the centroids that we find are no longer changing for a particular cluster. So for instance, if I establish that I want to work with 3 clusters, what this flowchart over here represents is that we've initialized the cluster centroids, which are 3. So we are going to compute the distance from one observation to each cluster, find the minimum distance, and then assign our observations to those clusters. Okay. And then after you've done that, we're going to compute the new clusters. Of course, here there is a loop again until we get to the last observation. So once we've gotten to the last observation, we'll calculate a new cluster centroid and compare this centroid to this. So if here we find 3 centroids and initially we had 3 centroids, we'll have considered that our iteration over here has converged. So we exit the loop and then we establish that 3 clusters and these are their parameters. Okay. And so finally, when it comes to evaluating the performance of our clusters, there are different indices. There's the Dan index and there's the David Baldwin index. I think there are other indices as well, which I may be missing out, but here I've provided some materials which you can refer to for more information. So basic overview is that a good BB index should be as low as possible. So think of it as an evaluation metric for supervised learning. And a good Dan index, or an index that shows that your clustering algorithm works well, should be as high as possible. So the possible range of Dan index is between 0 to infinity. So our objective is to maximize the Dan index. On the other hand, our intention or objective through this entire process is to minimize the DB index. Okay. So yes, basically that's a general overview of k-means clustering. So before I move on to the next section, which is implementing the algorithm, is there any other question so far? Okay, so I'll assume this none. Then proceed over to the implementation process. Okay, so these are the libraries that I'm going to use. Of course, NumPy and Pandas for handling data, Matplotlib for plotting, k-means for the clustering. So one good thing with the scikit-learn is that it comes with a pre-installed library called k-means that can be used to do all this with few lines of code. Then we're going to use one of the inbuilt datasets from scikit-learn, and finally, I think we'll use the matrices. So the data that I'm going to use is called iris data. So let me just put it first. So what iris data is that it's a collection of observations from 3 species of flowers. And I think there is Iris virginica, Iris setosa, and the other one I've forgotten. So each of these species has got 4 characteristics. That is the sepal length, sepal width, petal length, and petal width. So this is how you call your features and targets. Okay, so X are the 4 features that I've just mentioned, and then Y is the target, and this is the label of our iris dataset. So if I call a few samples of X, we'll see that we have an array here. It's a 2-dimensional array, I think. And no, it's n-dimensional. So we have 4 rows representing each of the 4 species. I mean, we have 4 columns representing each of the 4 characteristics. That is the sepal length, sepal width, petal length, and petal width. And then we are calling in the first 5 rows. Those are just 5 first samples. Now, if I call in the corresponding labels, we have 000. They've been encoded, but this is just one of the species. I think it's either Setosa, virginica, or forgotten the other. So if you call in the number of unique values in our Y variable, we'll see that there are the 3 species which I've just mentioned. So we may want to see the distribution of this data, so we can select 2 columns at random here to plot. So I'm going to select the sepal length versus sepal width, and specifically I want to plot total rows. So start with the first sepal length, and then sepal width. Save the title. Okay, so this is how the two compare. Of course, in the y-axis you have the sepal length, and the x-axis you have the sepal width. So sepal width. So I wanted to show you this first, so that much later on, when you've done the clustering, we'll repeat the same plot, but now instead of having a uniform blue color, we'll have colors that are distinguishable based on the cluster that the species exists in. So this is our data. So the next process, we want to implement the elbow method to help us identify the appropriate number of clusters in which we can categorize this data in. Of course, you know that since we are working with 3 species of flowers, it would be appropriate to cluster it into 3 categories. But for demonstration purposes, let's assume that this information is unknown. So we want first to create empty lists for the distortions and the inertia. So this is where we're going to put in the parameters that will be used to help us determine the optimum number of clusters. Then I'm going to define a range of clusters that you are interested in. So you can make a guess and say that the optimum number of clusters lies between 1 and 10 clusters. So I'm going to create a loop using this number of clusters. And then for each loop, for each value of clusters here, I'm going to call the k-means algorithm. And how do we call that? Simply do this. K-means model is equals to k-means. And then it takes in the number of clusters as the primary argument. So instead of defining a specific number, I just put in my k. So meaning it's going to iterate from k is equals to 1 to k is equals to 10. Now, for each of these models, say model instead of models, I'm going to fit it in my data. And then after fitting it, of course, now it's going to generate things like the centroids, the cluster distances, and such. So those distances are the ones that we're going to use to evaluate the appropriateness of different clusters over here. So I'm going to first call the first value, which is distortions. And as we said, distortions are basically the distance from like the average of the difference of the square difference between different cluster centers. So this is how you get that it's minimum. Because you have to minimize it. For that means the clusters. Okay, and then the distance that you are interested in is the Euclidean distance. You remember last time we had derived a formula for calculating it, so you can just go back to last lesson's tutorial if this escape you. So we want to do this along the first axis. Then we want to divide these distortions by the total number of observations in the data. So we call that. Then since we had an empty list, we're going to append these values there. And then you're going to repeat the same process for inertia. And it is simple. We just do this. Inertia. Okay. Inertia values. So I think that will be good. So if I call these distortion values and inertia values, it's just going to return a list of numbers here. Sorry for that. Okay. Let's see these two. So we have a list here, and if you observe keenly, you see that these values are kind of reducing. Of course, we can already make an inference and know that the optimum number of clusters should be somewhere between here and here, because these are the minimum. Our objective is to find the minimum, so these are the lowest values. But then by just inspecting these numbers, it may be difficult to actually determine the most appropriate. We can only make a guess. We can't make an educated guess, so to say. So if we call the inertia values as well, we're going to end up with another similar list. So if you look keenly, this time you have bigger numbers, and again they are trying to reduce. So again, we can also make a guess about the number of optimum clusters. You can see it's between 1, 2, maybe between 3 to 10. I'm sure. So now we can make a better guess by visualizing this distribution of both the inertial values and distortion values. And how do you do that? You do that by plotting something that's called an elbow plot. So basically, I'm going to plot my values of k here, and then I'll start with the distortion values. Establish this color here as black. Then the label will be elbow plot of some distortion values. So my y-axis, I want to put there the distortion cost, and then the x-axis, it's the number of clusters, brackets k. So now if I call this distortions, so you have this elbow plot over here. It resembles a human elbow, and you can see that between clusters 1 and 2, there's a very sharp decline in the distortion cost, and then from cluster 3, the decline sort of becomes more steady. So different people, different groups may have different interpretations of these clusters, but it's usually advised to pick the number of clusters where the elbow kinds of becomes less steep. So that can either be 2, 3, or 4, depending on how you choose that. But I would go with 3 because I already have prior knowledge that my data belongs to 3 distinct categories. If that were not the case, I could choose a number between 3 and maybe 4, 5, yeah, maybe 3 and 5. But since you already know the actual number of classes, we'll go with 3. So you can repeat the same process for inertial values as well. Here to the plot, okay. Then this time I'll use inertial values. So now for the inertial values, it's almost the same thing, but now our y-axis is a little bit different in the sense that we are not plotting this distortion cost. Again, the results are almost similar. We can see that the appropriate number of clusters is somewhere between 3 and 4. So again, I'll go with 3. So these two are kind of supplementing each other. If I don't know the appropriate number of clusters, then maybe I could do the distortion values and the inertial values, and if there's some sort of similarity between the two approaches, then I'll go with the common value. So basically, that's how you determine your optimum number of k. Okay, so after doing that, of course, you can now select your optimum number of k and cluster your data. So to do that, it's simple. Now find your model there. It's k-means and number of clusters. Now instead of putting in a variable, we can put in a determined number, 3 for our case. And then you want to fit this model data. And then finally you want to predict the clusters. So model.predict x. So what clusters here will return? It's going to return the cluster in which each of our observation belongs to. And if you look closely, you have 3 clusters that are almost uniform. So this bears a similar resemblance to the actual target. So you can see that we have like a certain number here of class 0, which is just represented as class 1. Then we have, of course, class 1, then class 2. But then the difference here is that this algorithm does not know exactly this category. So that's why you can see that you have 0, 0, then a 2, then 0, 0. While on this, we have like interrupted sequences of our respective categories. Okay, so this shows you that k-means is not as ideal as human labeling, but the accuracies are almost comparable. So we can do one more thing. We can now repeat this plotting over here, but this time we are going to use the clusters as our color indices so that we can distinguish these observations into their respective categories. So to do that, let's simply do a plt.scatter, and I'm going to take the first observation here, and the second observation, and then the color argument here will be the color map that we had defined earlier, and it's going to take an argument of the floats divided by 10. So then taking for I in clusters that we just predicted. So these clusters over here are just these ones. So now if I plot this, you can see that instead of just having a monocolor, we have a plot with 3 colors, although 2 may be indistinguishable. But you can see there's a red, orange, and I think maroon or purple, I'm not sure. So basically that's everything that, not everything, but the basics of k-means clustering. Of course, you can now go ahead and compute the David Baldwin score and the Dunn index of your clustering algorithm. But I want to leave that as an exercise for you. So up to that point, I don't know, do you have any other question? Is there any part that wasn't clear that you may want me to repeat? Okay, so I'm assuming there's none. So just to mention, here we have used the Euclidean distance, but in your further reading, you will encounter the distances as well. There's the Minkowski distance, then I think there's the Haversine distance, and then there's the weighted Minkowski distance. Of course, different distances will perform differently. So in your personal reading, you may try to change this and see how it affects the results. And then another thing is that we are using an implementation by scikit-learn. Of course, you can do this using NumPy and other libraries as well, which I would encourage you to try that out. I'll attach another notebook that has that. So the good thing with implementing your own k-means is that you may experiment with different algorithms or with different distances. So, for instance, if you've been given data that is, let me say, specific to your field, and since I'm from the physics background, I'm going to give an example using a physics example. So assuming that I've been given a distance, I've been given data, but this data is not sepal length versus sepal width. Instead, it's something, say, atom 1 on the x-axis and atom 2 on the y-axis. Of course, apart from the distribution on this Cartesian coordinate, I know from my background that we have some electrostatic forces or gravitational attraction between these two atoms or particles. So instead of just talking the Euclidean distance, I may define my own custom distance, say gravity-based distance, and it will be based on empirical relationships between these two atoms over here. So I can try that and then compare it with the performance of the Euclidean model. And in many cases, I found that if I create my own custom k-means using my own custom distance metric over here, the performance tends to be better than that of the Euclidean distance. So I'm going to provide a notebook that highlights that in a better way. So yeah, that's it for today. Since there's no question, I want to stop at that point. Thank you.